Hello, ChE 191 students. I hope you and your families are safe and well in this unprecedented pandemic. Even though we are facing a lot of problems, I strongly believe that education should not be hampered by them. So I am grateful to be given this opportunity to share with you one of my research interests through online lectures. Please allow me to introduce myself. I am Eliezer L. Vivas. I am an alumnus of the UPLB Chemical Engineering Department. When I was in college, my thesis advisor was Dr. Catalino G. Alfafara, and my thesis co-advisor was Dr. Veronica P. Migo. So currently, I am a PhD student of the Environmental Engineering Department of Busan National University here in Busan, South Korea. So 안녕하세요. So I was invited to give two lectures, and this will be my first lecture entitled Electrospun Composite Nanofiber Adsorbents for Water Treatment. At the end of this lecture, you are expected to meet the following. You should be able to 1. Explain the electrospinning process for nanofiber production. 2. Assess theoretically how electrospinning variables affect the quality of nanofibers. And 3. Illustrate the potential of nanofibers in treating polluted waters by adsorption. This will be the flow of my lecture. If there is anything unclear, then you know the drill. You are free to pause, rewind, and play. I also provided a supplemental reading material, which will help you better understand and appreciate the lecture due to limited time. Please ask Dr. Migo for the copy of the supplemental reading material. Before I proceed with the lecture proper, please allow me to briefly introduce Busan National University and the department and laboratory where I am a part of. Busan National University is the first national university in South Korea. It was established on May 15, 1946. The university continuously strives to be a regional hub of modernization in various fields for the betterment of its students and community. It is located in Busan Metropolitan City, which is the second most populous city of South Korea. Believe me when I say that Busan is a peaceful city. Do not worry, there are no zombies here. You can check more about PNU by checking out its promotional video through the YouTube link below. These are the representative pictures of PNU in different seasons. We have winter, spring, summer, and fall. It is already autumn here, or fall, by the time you are viewing this video. PNU's Environmental Engineering Department is composed of outstanding professors who are very active in their respective research interests. Currently, our department has 9 professors, and I am one of the advisees of Professor Kukcho. I am one of the PhD students of the Laboratory of Particle and Sustainable Technology, which is headed by Professor Kukcho. Presently, our laboratory has 2 major research interests. One is the investigation of particulate matter pollution. This research area requires fused knowledge on atmospheric chemistry, physics, statistics, mathematical modeling, and engineering. The other, where I am working on, is the development of functional particles or nanostructured composite adsorbents for the removal of toxic, heavy, and precious metals from water. This is our team currently, and this guy is me. Let us now start the lecture proper. Nanofibers are fibers with average fiber diameter of less than 1 micrometer. Some references, however, assert diameter of less than or equal to 500 nanometers. This image is a sample of, shows you a sample of nanofibers. This one compares the size of a strand of human hair and nanofibers. Obviously, you could see that the nanofibers are significantly smaller than the human hair. Nanofibers can be produced from different polymers having different properties and potential applications. Examples of electrospinable polymers are polyvinyl alcohol or PVA, polysulfone or PSF, polyacrylonitrile or PAN, and polymethyl methacrylate PMMA, the biodegradable polycaprolactone or PCl, and polyethylene covinyl acetate or PEVA. Nanofibers have unique properties, such as large surface area to volume ratio, notable mechanical and chemical strengths, high porosity, good flexibility in functionalization and or chemical modification, and surface hydrophilicity or hydrophobicity. When we say good flexibility in functionalization or chemical modification, let's try to explain that using PAN as an example. You can see that PAN has a nitrile group. It has a carbon-nitrogen triple bond, and this triple bond is open for reduction and oxidation reactions. And thus, through different reactions, you can change the functional group, and then it would have modified properties. Now, how do we produce nanofibers? There are three known established processes by which nanofibers are fabricated. They are self-assembly, phase separation, and electrospinning. Among these three, electrospinning is considered the superior, as this process is cost-effective. It is capable of producing long continuous fibers with tailorable properties, and it is capable of processing a plethora of polymers. Its limitations, however, could be addressed by fine-tuning various electrospinning variables, and these variables will be discussed later in this lecture. The electrospinning process is the most common and versatile technique in nanofiber fabrication. This process applies high voltage to form fibers from polymer solutions or melts. So through application of high voltage, it will create an electric field between a droplet of a polymer solution at the tip of a needle and a collector. One electrode of the voltage source is placed into the solution, and the other is connected to the collector. A droplet of the polymer solution then forms at the tip of the capillary, creating a point known as the Taylor cone. And the geometry of the Taylor cone would depend on surface tension to electrostatic repulsion ratio. When the electrostatic force overcomes the surface tension of the drop, a charged continuous jet of solution is ejected from the cone. So this region is known as is characterized by ohmic flow, and there is slow acceleration. Then from this region, from this part, the charged jet now transforms into fibers. And as the fibers fly from this region going to the collector, the solvent molecules rapidly evaporates. Hence, this region is known as a convective flow, is characterized by convective flow and rapid acceleration, or specifically rapid liquid to solid transition. Because from the charged jet of solution, which is liquid, then it will transform into fibers. So fibers are solid once they become dry. If you magnify the polymer solution that is charged with high voltage, then this is what is happening at the tip of the spinneret. So the polymer molecules becomes negatively charged, and they have now, they will experience repulsive forces. And due to repulsion, as it travels from the tip going to the collector, they will like separate. The solvent molecules will start evaporating, and also the charged jet of the solution will separate into fibers because the polymers are experiencing high repulsion due to the negative charges. So they will repel each other, and they will form nanofibers. This photo is actually the shows the electrospinning system that I use in my experiments in making nanofibers. Typically, an electrospinning system is composed, of course, of the high voltage power supply, spinneret, here too, and higher magnification of that is this one. We have an automated syringe pump and a collector. In our case, we use a metal rotating mandrel because when it's moving, when you have a metal rotating mandrel and not a flat plate stationary collector, then the spinning will, this is like moving, so it's spinning. So when it's spinning, it will also help in fine-tuning or creating quality fibers. This is an actual electrospinning process. So we have the spinneret, and this is the needle, and this is the tip of that, the tip of the spinneret. It's not very clear, but you would see here there's some solidification happening here because actually this is not a pure polymer solution. This has some inorganic adsorbents. And then, but you would see here like a solid line, and then suddenly a cone-like spray. But actually, these are fibers, the fibers which are from the jet. Then the polymer molecules, as I discussed earlier, they will repel each other to form fibers until they reach the collector here. So this is actually a mat of nanofibers. I believe everyone knows cotton candy, right? Actually, cotton candy is made up of brittle fibers of cooled molten syrup. If you are familiar on how cotton candy is made, then understanding the electrospinning process would be easier for you. The major difference is the type of applied energy. Cotton candy production requires heat energy, while electrospinning needs electric potential energy. Using a cotton candy maker, Syrup is heated until it melts. Then the melt is spun. So this part is actually a moving element of the cotton candy maker, and there are holes here. So the melt is spun out through tiny holes here, and as the fiber spins, it is pulled thinner and thinner until it cools and hardens. Then the vendor of the cotton candy would now collect these um, fibers, or what we call cotton candy, I think using a wooden stick. And then, if I remember it right, when I was a child, he would put it in plastic and then give it to us. So before I proceed to the next slide, here's a question for you to ponder on. Mm, is the cotton candy made up of nanofibers of syrup? I will leave this question as your assignment. You don't need to answer it or send me an email for and give me the answer. You don't have to. To fabricate nanofibers from polymer solutions or melts using an electrospinning system, one needs to consider several electrospinning variables which affect the process. These factors are classified typically into three groups. One, processing parameters, which include applied electric field, needle to collector distance, flow rate, and needle diameter. Second, solution parameters, which include solvent, or the type of solvent, polymer concentration, viscosity, and solution conductivity. And third, environmental or ambient parameters, which include humidity and temperature. If you have a target properties of your nanofibers for a particular application, so you have desired not only properties but structure, fiber diameter, then you really need to fine-tune these factors for you to achieve that. And these parameters, I mean the influence on the electrospinning process, I will tackle them in the next few slides. The first group of electrospinning variables that I will discuss is processing parameters. There is a critical value of applied voltage for a particular polymer to be electrospun into nanofibers. There is no single applied voltage that could electrospin a plethora of polymers into quality nanofibers. The formation of smaller diameter nanofibers is possible due to the increase of the applied voltage, because this increase in applied voltage will cause stretching of the polymer solution in correlation with the charge repulsion within the polymer jet. If you increase the applied voltage beyond a certain critical value, then bead formation or beaded nanofibers will happen, as shown in these pictures. Beaded nanofibers are considered poor quality fibers. Normally, quality fibers should be uniform and beadless. However, there are some researchers who intentionally produce beaded nanofibers because their target application requires such morphology. The next one is needle to collector distance. In some textbooks or research papers, it is known as the tip to collector distance, or TCD. From the name itself, it is the distance from the tip of the spinneret to the surface of your collector, regardless of the type of the collector, be it a flat plate stationary collector or a rotating mandrel collector. This distance varies for different polymer solvent systems, and it greatly affects the nanofiber morphology, specifically the average diameter of your nanofibers. A critical distance for a particular polymer solvent system should be maintained to produce smooth and uniform nanofibers. If that critical distance will not be maintained, or you don't know that critical distance, then you will end up with beaded nanofibers, or you will not have no, you will not produce nanofibers at all. Third one is solution flow rate. Like the two other variables, there's also a critical value for flow rate for a certain polymer solution. If your target, of course, is a quality nanofiber, then it should be uniform and it should be beadless. Then you need to determine that critical flow rate. If the flow rate is less than that critical value, then you would form uniform beadless nanofibers. However, if the flow rate goes beyond that critical value, then beaded nanofibers will be produced. If you are, of course, we are targeting quality nanofibers, so we don't want beaded nanofibers, so we need to determine the minimum flow rate at which there would be a balance between leaving polymeric solution and its replacement with a new one during jet formation. As shown in this figure is the formation of various jets with increasing flow rate of nylon 6 polymer solution. The leftmost image gives a very good geometry of the jet, cone jet, and then this one, although it's also a cone jet, this rightmost image also has a cone jet, but it has unspun droplets. So definitely this type of jet would lead to poor quality nanofibers, and it will adversely affect the properties of your nanofibers. The second group of electrospinning variables is solution parameters. Polymer concentration and solution viscosity is normally considered as one electrospinning variable because polymer concentration directly influences the viscosity of the solution. When the polymer concentration is low, the applied electric field and surface tension would cause beading of the nanofibers. If you increase the concentration, then viscosity of the solution will increase and the polymer chain entanglement increases. This phenomenon will then overcome surface tension, resulting in fine nanofibers. However, further increasing the concentration will result in bead formations, and we don't want beaded nanofibers because they are actually poor quality nanofibers. The next one is solution conductivity. If you have a low conductivity solution, then you will form chargeless droplet surface. You will not observe any Taylor cone, hence no nanofiber will be produced. If you increase conductivity to a certain critical value, then it will increase the droplet surface charge, and you will observe Taylor cone formation at the spinneret tip. And you can say, and definitely electrospinning will proceed. But take note that even if you observe Taylor cone formation, or Taylor cone formation does not guarantee quality nanofiber production. It means you still need to do further fine-tuning until you achieve your quality nanofibers. Above the critical conductivity level, you will not see any Taylor cone formation, and electrospinning will not proceed. This figure shows images or an illustration of bead-free and beaded nanofibers. And in that nanofiber, you would see the interaction between the solvent molecules and polymer molecules. This illustration shows the variation in morphology of polyethylene oxide nanofibers with increasing viscosity. So as the viscosity increases from left to right, the morphology of the nanofiber becomes better. So the rightmost image shows the best or the high performance nanofibers, while the first three from the left are beaded nanofibers. Choosing the right solvent is very important in electrospinning. The solvent used in polymer solution preparation has significant effect on the electrospinability of a polymer. Solvent properties have great influence on nanofiber diameter. If the polymer and the solvent molecules have good intermolecular interaction, then expect that you will be able to produce quality nanofibers in electrospinning. You have to take note that the intermolecular interaction could either be attractive or repulsive, and it is actually the solvent which dictates this interaction. The solvent properties that you have to consider are volatility, vapor pressure, surface tension, dielectric constant, and boiling point. Volatility plays a significant role in the formation of nanostructures because it influences the liquid-solid transition or the phase separation process during electrospinning. Vapor pressure, on the other hand, would determine the solvent evaporation rate and drying time of electrospun nanofibers. Surface tension, dielectric constant, and boiling point are the other properties that you should consider in solvent selection. They may not be as important as volatility and vapor pressure, but you still have to consider them. In this illustration, you would see it's an illustration of the polymer-solvent intermolecular interaction, wherein the yellow circles are the solvent molecules, and the blue lines are actually the polymer chains. Image A shows the polymer molecules in its solid state just after being added to a solvent. So there is no polymer-solvent intermolecular interaction yet. Image B shows a swollen polymeric gel, wherein the polymer chains and the solvent molecules are starting to have an interaction. And if the polymer and the solvent have an attractive intermolecular interaction, then you should see, then image C is representative of that, which is a solvated polymer molecules dispersed into a solution. So if your polymer solvent or your polymer solution have good polymer solvent intermolecular interaction as represented or illustrated by image C, then the chances of your nanofiber being of good quality is high. The last group of electrospinning variables which also influence the diameter and morphology of nanofibers is ambient parameters. Humidity could control the solidification process of the charged jet, but this solidification is dependent on the chemical nature of the polymer. When you say chemical nature, the polymer could either be hydrophobic or hydrophilic. If the polymer is hydrophobic and there is high humidity, then during electrospinning, you will produce poor quality fibers, beaded and then unspun droplets. Humidity can also cause the fabrication of porous nanofibers when you are using a blend of solvents in the dissolution of your polymer. On the other hand, temperature influences the rate of solvent evaporation and solution viscosity. As the temperature increases, the rate of solvent evaporation also increases. However, solution viscosity decreases. The images here below shows Electrospun PMMA nanofibers. All are of good quality, but they were electrospun at different humidity ranges. The nanofibers in images C, D, and F have good average fiber diameter, but they have porous morphology. This slide summarizes the electrospinning variables and their influences on fiber morphology as discussed in the previous slides. This is an illustrative summary of the electrospinning variables and their influences in producing low performance or high performance fibers. How do we confirm if our nanofibers are of good quality? The answer is we conduct nanofiber characterization. There are 3 types of characterization: geometrical, chemical, and mechanical. In geometrical characterization, we can determine the nanofiber diameter, diameter distribution, orientation, and morphology. The techniques employed are scanning electron microscopy, field emission SEM, transmission electron microscopy, and atomic force microscopy. At the right side, you would see examples of the SEM, FESEM, TEM, and AFM images of quality nanofibers. In chemical characterization, we can detect the structure and intermolecular interactions. The techniques used are Fourier transform infrared spectroscopy, or FTIR, and nuclear magnetic resonance, or NMR. So, for FTIR analysis, this is a sample result. You can get this kind of peaks which correspond to particular functional groups. And this is a sample of an NMR spectra, and it would also show you the functional groups present in your polymeric nanofibers. In mechanical characterization, we will be able to measure the tensile strength, elongation, and Young's modulus. This is an example of the graph comparing the tensile strength, or showing the tensile strength, elongation, and Young's modulus of a polymer loaded with an inorganic material. So the instrument used to measure these mechanical properties is known as a Universal Testing Machine, or UTM. Polymer nanofibers have a wide array of applications, but for this lecture, I'm going to touch on the potentials of polymer nanofibers in environmental applications. Summarized in this table are polymer nanofibers which were investigated for different applications. So you don't need to memorize these polymer nanofibers and their specific applications, because a particular polymer nanofiber is not limited to one application. This pie chart shows that nanofibers are widely used in developing sensors and photocatalysts for various environmental applications. In this graph, from 2002 to 2012, the literature published on the applications of nanofibers in environmental field significantly increased. This suggested that there is a strong demand on the environmental applications of nanofibers. The need for clean water is an ever-growing concern in underdeveloped countries. This is projected to be a major stressor on modern economies in the future. Currently, there are many investigations in addressing this environmental challenge using nanofibrous membranes. The nanofibers can be functionalized or altered into different forms so they can be used in water liquid filtration, adsorption of water pollutants, oil spill cleanup, self-cleaning, and other environmental applications. As mentioned in the previous slide, one of the potential applications of nanofibers is its use in the adsorption of water pollutants to address the need for clean water, which is actually a global concern. So this is actually just a review on adsorption process. So adsorption is the deposition of chemical species onto the surface of a material. So the materials or chemical species being adsorbed is called adsorbate, as shown in this figure. And the surface at which adsorption occurs is known as the adsorbent. So examples of adsorbents are clay, silica, gel, colloids, and even metals. So there are two types of adsorption. We have physical adsorption or physisorption, which involves the adsorption via weak van der Waals forces, and it doesn't have any specificity. And the other one is chemical adsorption or chemisorption, wherein adsorption happens through chemical bonding, as shown in these two figures. So adsorption is a promising alternative water decontamination technology. However, because it typically employs adsorbent powders, it is prone to particle loss, and they are difficult to recover after use. And using powdered adsorbents limits the field application of adsorption. So this is where nanofibers comes in. Recovery of saturated adsorbent powders in water remains a problem. One of the proven solutions is the immobilization of adsorbent particles using nanofibers. So we make a composite solution of the polymer and the adsorbent particles. And once we achieve a homogeneous solution, we can electrospin it into nanofiber adsorbents. Like these 4 examples of nanofiber adsorbents, which were used for metal uptake and even for dye removal. In my next lecture, I will be sharing to you one of the newest NF-supported adsorbent. To close my first lecture, I am leaving you with these review questions. Again, please give quality time in reading the supplemental material that I provided to Dr. Migo. Thank you for listening. If you have any questions, I will be glad to answer them through email.